The purpose of this lab is to study the behavior of the bottom of an extended slinky once its top is dropped from rest. To do so, I use concepts of forces and Newton's second law. In the experiment, gravity, tension, and drag all had effects on the slinky. In the case of this lab, drag is a resistance force on the falling object represented by the formula -b times velocity squared in the direction of velocity. In the first part of the lab, I studied a video of a slinky falling from rest and used the application tracker to measure the slinky's motion. In the second part, I constructed a simulation of the slinky based off of my data from part 1. In the end, properties of forces can be used to explain the motion of the slinky. In the first part of the lab, I studied a video of the slinky falling from rest using the application tracker. For the initial conditions of the bottom of the slinky, it was suspended at rest about half a meter above the ground, which I marked as the origin in the dataset. Its mass is about 0.2 kilograms. By measuring the position of the bottom of the slinky throughout the video, it can be seen that it remains at its initial position until about 5 seconds into the slow motion video when the top of the slinky meets the bottom. Then it falls to the ground. For the second part of the lab, I used the position data from part 1 to construct a simulation. I described the initial conditions for the slinky as well as added constants for the gravitational force and drag force. To simulate the motion of the bottom of the slinky before it began falling, I created a while loop that lasts about 5 seconds. In the while loop, I added up each of the forces acting in this time, gravity and tension, to get a net force. Then I used the net force and Newton's second law to calculate and update the velocity and position of the slinky. Gravity and tension should cancel out, keeping the slinky at the origin. To simulate the motion of the bottom of the slinky after it began falling, I created a while loop that lasts about 3 seconds. In this while loop, I added up each force acting for the rest of the time, gravity and drag, to get a new net force. Then I use the Newton's second law to calculate and update the velocity and position of the slinky. In this loop, there is no tension to cancel out gravity, therefore there will be motion. By running the code, the mass sits still for about 5 seconds and then moves downward for the rest of the simulation. By comparing data from both the observed video and the simulation, the computation data is seen to accurately recreate the motion in the real-world model. They both have a segment where there is no motion and a segment where there is motion. In this lab, there were possible cases of error. One possible source of error is that I could have inaccurately scaled the observations I made in Tracker. Another source of error is that the slow motion aspect of the video made it difficult to accurately determine a coefficient for drag. So why does the bottom of the slinky act this way? Just after the top of the slinky is released, the bottom of the slinky remains still until it is connected with the top of the slinky again. This happens to the bottom of the slinky because it has a tension force created by the top of the slinky that cancels out its gravitational force. Since the net force at the bottom of the slinky is 0, its motion cannot change and it is suspended in air. This lab shows how forces and Newton's second law can accurately predict the motion of everyday objects.